So, welcome back. We were discussing about polymers. We will keep this discussion going on today, and we will discuss some of the other important terms and issues that you would encounter with polymers when you deal with them. So, most of these polymers, so polymers can be classified. So, we discussed this homopolymer and the copolymers and others, but we also discussed that you have these different forms, the straight, the linear macromolecule and the branched macromolecule. But overall, these polymers can be classified into two general broad engineering names, and one is called a thermoplastic. And another is called a thermoset. And in the under the thermoplastics, you can also have crystalline and amorphous polymers. Amorphous. So, what gives rise to these different forms? Now, when I say amorphous, it is an indication that when you let us say take a polymer and you cool it down, then what is the state of the cooled solid body that you are getting, the condensed form. In an amorphous form, you would have a lot of disorder within the molecules, whereas a crystalline name usually refers to some kind of structure that is there amongst the molecules. So, but under thermoset I did not draw any of this. So, why is that? So, thermosetting, and there is a reason for that, and the reason is that the thermosetting, or which is also called the cross-linked polymers, are usually formed under catalytic conditions of heat and pressure. And the reason we are mentioning this formation is because what this formation does is during the polymerization process, it causes the formation of covalent bonds between individual chains. Okay. So, covalent bonds exist between individual chains. So, if you were to look, if you were to take go down to the atomic scale, what you would find is, let us say you have a polymer, this is a chain, and let us say this is another chain. Now, at some point they have come into close contact with each other, it is right here. In a thermoset polymer or cross-linked polymer, at this location you have another covalent bond between this chain and the other chain. Okay. And that what does is basically now what you are looking at is a large molecule, an even larger macromolecule than the original polymer itself, because the polymers have now been cross-linked with each other. So, they are covalently bonded. So, breaking the bonds is going to take a lot of energy, and in contrast to the covalently bonded cross-linked polymers exists a different class. Now, remember when we are discussing bonds, we had discussed that there are two types of bonds, right. So, we will just quickly go back to that. right. So, we had said that there are in atomic bonds there are two types of bonds, the primary and the secondary type of bonds. So, when we come back to our system like this, you can have at this location you can either have a primary bond or a secondary bond, okay. And that gives rise to the difference between the two polymers. If you have a secondary bond, you end up with a thermoplastic, because in that case the bonds are weaker bonds and those bonds can be broken with less energy. Whereas, for the thermoplastic case, thermoset case, there exists covalent bonds between the different polymer chains, right. How many cross links, we have not said that. So, that itself can vary, but the moment you have covalent bonds, you end up with it requires you a lot, it requires a lot of energy input to break these bonds. So, most of the thermosetting polymers exist as solid bodies at normal room temperature and pressure. Example would be bakelite, rubber. Whereas, for the other case, the actually maybe I should define it right now. So, the other case is the thermoplastics. Right. So, thermoplastics have only secondary bonds between chains as opposed to thermosets which have primary bonds. So, this location of overlap, location of two chains coming in close contact, so at this location you can have either a primary bond or a secondary bond, and that makes the difference between the two. So, thermoplastics, the chains can also slide past each other, and that is why these plastics or the thermoplastics can be melted and even molded. So, thermoplastic polymers can be melted and even molded, whereas the thermosets cannot be melted in a general sense. Okay. And you want to note that, so note that cross linking is different than chain branching. Because in a chain branching situation, the branches are supposed to be small, okay, speak to each other. So, let us contrast one more time these two. So, you have the thermoplastics You have the thermosets, and within the thermoplastics you can have a linear chain. So, this is linear, or you can have a branch system. So, this is your branched. But in this case, in this case of the thermosets, the moment you have these polymer molecules, you can have, these are, we will use this, these are all locations of covalent bonding. And the number of covalent bonds can be high or low, and that depends upon how you have manufactured them. So, you can have another case where a very similar situation, let us say, and here the number of covalent bonds are lower. Okay. So, this will be called a heavily cross linked polymer thermoset, and this is a lightly cross linked. So, we can see that the very fact that your molecule is becoming large is leading to so many issues and so many other configurations that are possible, right. So, all these complications simply arise because now your molecule is large. So, the variation that can be there in the molecular structure is also becoming large, and we have not even talked about isomerism. Right. So, you can have molecules that exist in different isomeric forms, and that would also lead to a whole different set of conformations that are possible. So, we are not, isomerism is also an issue, but we are not going to discuss that here. So, let us since we are trying to familiarize ourselves with polymer literature, we are going through all the different terms that are important in this particular area, and let us just go ahead and familiarize ourselves with a couple of more. So, for example, in an industrial setting you would have something called a blend, okay, and a blend is a mixture of two or more polymers, obviously different polymers, right. Then you have terms like LDPE, which is used for low density, in this case it is low density polyethylene. We have HDPE, and the reason we are going through all this these sundry facts is because just to give you an idea that the moment you have these large molecules, how many different complications are possible, and that can lead to all these different issues that you have to take care of. So, high density, and if you place a U here, then it becomes ultra high density. So, there is something called UHDPE. So, changing the structure is going to lead to all these. So, I am not going to copy this. So, just I will say ultra high density polyethylene. Thermosetting polymers, some examples perhaps. So, thermosetting, polymers, examples are, the common examples for this are bakelite, polyesters. I am sure you have heard of the term polyester, right? Goes into making of clothes sometimes. Polyurethane. Examples of amorphous thermoplastics are polyvinyl chloride, part of the vinyl chloride, the vinyl polymers, the polyvinyl chloride, sort of PVC, polystyrene, PS. So, polystyrene is something you might have encountered quite a bit. Polymethacrylate, PMMA, and polycarbonate. And examples of crystalline thermoplastics, would be polypropylene, polyamides, etc. So, what we have done is we have encountered a lot of different terminologies with respect to polymers, specifically some of the engineering related terminology, thermoplastics, thermoset, and so we have seen that this cross linking or not the presence of the secondary or primary bond can be an important classifier here. But what about the individual chain itself? Okay. So, we have not discussed isomerism so much, but the individual chain can exist in a number of different forms, right. So, the individual polymer chain, if you, so the carbon, so I am just drawing the carbon backbone. Okay. So, if this is the carbon backbone, you might recall that this angle has to be 109 degrees approximately. So, a linear or fully extended chain would have a backbone like this. So, this is your linear, sorry, is a linear molecule, sorry, fully extended polyethylene chain. But you do not expect atoms. So, this is a crude diagram because the angles are always supposed to be 109 degrees. Now, atoms are always moving, right? They are never stationary. Right? So, at any finite temperature they cannot remain stationary. So, there is always the tendency to move, and we know that the single carbon carbon bond allows for rotation. So, once it allows for rotation, you can actually have rotations of this that are possible. So, for example, in a due to this thermal motion of the atoms itself, okay, maybe I will just draw it a little bit down. So, due to the thermal motion of the atoms, this I have to draw like that, but the second one I can draw it in this fashion. So, this bond has undergone rotation. this is and if all the other bonds are also undergoing rotation, you can end up with a chain like this. Right. So, this keeps on going. So, your final chain, which is going to consist of a very, very large number of bonds, can look like this convoluted chain, and this is what usually if you take a polymer molecule and when it is in solution or when it is in a even in solid phase, this chain molecule will be in some convoluted form, if specifically if the number of degree of polymerization is very, very high. So, it is not never going to be this extended molecule, right. So, let us say your degree of polymerization is 10,000, right. So, the carbon carbon bond we know is about Armstrong. So, that is 10 to the power minus 10. Right. So, if you have a degree of polymerization of 10,000 or 10 to the power 4, then if the chain were to be fully elongated, it would be of a length of 10 to the power minus 10 into 10 to the power 4, which is 10 to the power minus 6. So, that is almost 1 that is 1 micron. 1 micron, at what stage can you start seeing with your eye? About 100 microns is something that is in a human eye's resolution, and 10 to 10,000 we just discussed is a small number for a polymerization, right. So, if you have a polymer chain whose degree of polymerization is, now let us say take a million, 10 to the power 6, that would be 100 microns. So, if you have a polymer chain and its degree of polymerization is 1 million, then if you were able to stretch it out, you would actually be able to see it with your naked eye. Right. So, one molecule you will be able to, single molecule will be something that would be within the grasp of your human eye's resolution, and obviously a million is small, right. So, you have chains which have a billion up to degree of polymerization. Then if you stretch that out, then that could be 10 to the power 3 microns, right. This is almost that's millimeter. So, you can actually see it on a small scale. So, but a polymer is never going to be that big, right, because there is no force, you need something to stretch it out for that. Polymers are always coiled up. A human DNA is a polymer with a very large degree of polymerization. So, if all of them had to be of that, if they were stretched out, then your average human cell would have to be much bigger than a micron, right, or sorry, a millimeter. Right. So, we know that that does not happen. So, in reality, in the natural state, the polymer molecule never exists as an extended chain, but rather as a crumpled up ball. Okay. And the important question is then that what is the size of this ball? So, that is something that we will see in the next class. Okay. So, we will end today's class here, and in the next class we will just try to see discuss a little bit more on polymers and some of the other classes of soft materials. Okay. So, we will stop here today.